So yeah, so I found the error. It was a stupid error. But yeah, it's very risky to do such a long proof without a note, you know. Yeah, the error is just that, you know, when you have like, so basically the scalar product, so the Dirichlet product between the operators is trace of A B dagger, right? So then if they're proportional, then it's really that A is proportional to B, right? Not to B dagger. So here we have the dagger on the left. Because in this expression, I just took this operator and this operator when we have the trace. But actually, we should take the conjugate of this as a proportionality because it's really the Dirichlet product between A and B. So actually, the correct equation here at this step would be just, as I told you, basically, was a guess, was just to have the conjugate here, right? So it will be like this, with this one, just all the orders changed, right? So let's just change it for the correct one. So this, in other words, the real one is with the dagger here. Okay, and now we can get to the point, I believe. Because, so if you just write it, this means that this P1 element square root is proportional to sigma minus 1/2 to this W. No, again. So all the order was changed. Rho K. All right. But of course, we also used the fact, but now we can also use this thing as I started to do last hour. So we've seen that this operator that appears in the fidelity, it's like this, or this one with the absolute value, or and we use this W here is precisely the one which appears in the polar decomposition. So in particular, we have this relation. This is just the polar decomposition of this which we use, and we can just conjugate it because this is invariant of the conjugate, right? It's a remission, and then we get that this thing is equal to this thing, or in other words, W. So from these two things, W square root of rho square root of sigma is equal to our story here. This. So we can pass sigma on the other side since we assume it's invertible anyway, right? And we also have this relation here, sigma minus 1/2 with a 1 here. Okay. Finally, the idea is just to plug it here, right? So we plug it here, and then we see what we get. And when we plug it here, so basically I just replace these two guys by the square root expression. We get, okay, right? We get that EK, the P1 element, is proportional to sigma minus 1/2 times, here we get our story. So square root of sigma, without square root, so rho, square root of sigma times sigma minus 1/2 square root of EK. Okay, and let's remove that. All right, and that's basically it. Because with now why this is nice, because we have EK here and we have EK here on the other side. So this relation basically just means that it's satisfied whenever EK satisfies. So this is basically just identity here, right? So we can just put it on the same side. This equation is satisfied whenever identity minus alpha k then sigma minus 1/2. And this very nasty, but nevertheless Hermitian expression here, right? EK is equal to 0. Okay. So it's almost over. Don't worry. So if you define this thing here as an Hermitian operator M, because it's Hermitian, right? You can see it's just symmetric. So it's just a product of Hermitian operators which is symmetric. So obviously it's Hermitian. Then we just get something like identity minus alpha k m square root of ek is equal to 0. In particular, now we can just diagonalize this m because it's Hermitian. And so m can be, so we can just express, which takes the basis which is the eigenbasis of m, and then we just write m as being a sum of some, I don't know, lambda k, k. Okay. And then if you plug it back, then it's really easy to see what is the right choice of the POM elements, which make the classical fidelity match the quantum fidelity, because this is just identity minus alpha k. Well, let's put a g here. Sum of j square root of ek equal to 0 for each k. But we can just take, basically it's clear now. Let's just take a POM element, which is a basis in the measurement in the eigenbasis of. You see, we just take POM now. Ek is just a measurement precisely in the eigenbasis of this operator for, sorry, this should be k. K equal to 0 to the dimension. Well, k equal to 0 to n. Yes, because if you do this, then, so if you say, if you do the measurement in this basis which diagonalizes m, then we precisely get here kk. So this thing becomes identity minus alpha k, here is a lambda j, lambda k, kk, okay. Sorry, not identity, of course, but k. And this will be 0 if we choose alpha k equal to, so this is equal to 0 if we set alpha k is equal to 1 over lambda k. Right? So what does it mean in other words? We found the condition where if we take this ek, which is precisely measurement in the eigenbasis of this operator m, then we satisfy this proportionality condition before, and then we basically show that this Cauchy-Schwarz inequality is just saturated, right? Because all the operators are proportional in for all cases. Right? Do you agree with me? So is it clear?
Yeah.
Yeah. So in other words, in summary, the conclusion is this operator m. Remember, it was something like this, minus 1/2. So it was something a bit ugly. 1/2, right? An Hermitian operator. Then a measurement. Wait, a measurement in the eigenbasis of m. So POM elements. Well, this case, just projectors. Then precisely we have f of the quantum states is equal to the fidelity of the probability distributions, p and. So yeah, that's it. Nice. Ah, no, wait. This was for invertible. Yes, just one short. So this we here you see, to do this we need to invert the density matrix. So we just need one small step to prove this for non-invertible, but this is actually kind of simple. Why? Because yes. So yeah, let's just take just to really be pedantic, let's prove everything. So for non-invertible, it's also simple because now assume if so second case would be that sigma is non-invertible, and then well, basically then it means what? And it means that sigma is just it has a part which is kind of invertible, right? So all the eigenvalues which are not equal to 0. Let's put sigma overline like this, and then zeros. Okay. Yes, but then what happens is when we talk about the fidelity, then the fidelity between sigma and rho, then it's just equal to, well, so you can just use the fact that, okay, so just use this expression. So it's the trace of the square root of this block diagonal structure thing. So we'll have square root here, sigma 0, 0, 0, right? Then we have rho here. So we have rho 1, rho 2, and some coherence. I just write rho in the same basis where I wrote sigma, and the same thing here. So you see that if you make this product like this block structure, what will happen is that at the end we'll just get here its trace. We just use it. So since here we get zeros everywhere, at the end this is just trace of an operator which is square root of rho bar, rho square root of rho bar, 0 zeros. Okay. In other words, we could just use it for this rho 1, right? So this is like formally it looks like the fidelity between rho bar. So this thing is equal to fidelity between rho bar and rho 1, which is not necessarily normalized, but nevertheless we can write it down. And then we have the same story then. Okay. So since these two fidelities are equal, here we just have zeros. So when we take the trace, it will just be 0. So now if you look on this expression, in this expression, sigma bar is invertible. So we can just apply the proof from before. Okay? Good. So this is just a short remark. And the big conclusion is that we managed to prove that this fidelity now indeed satisfies this. So the fidelity between the states is indeed equal to the minimal one for all P of n's between the probability distributions. Okay, and this is it's a long proof, but it will be important because this fidelity we will use it not the fidelity, but when we talk about the Fisher information, actually the nicest way to define it, at least for me, is really as a kind of expansion of fidelity for small distances between states. So then it will be very handy to use this relation between the fidelity between the state and the fidelity between the obtained distributions, right? So I think it's not an hour lost, even so the proof is a bit technical and maybe it was not so enjoyable for you, I don't know. Yes, so, but now we have it, okay? So we can just continue and with nice stuff. So okay, first thing we can see now is what does it imply for as the properties of fidelity? Well, first thing is remember we had this processing inequality. Processing inequality. Do you remember what it was? For trace distance? No? I think I should remember it. No? So so if processing inequality doesn't recall you anything? Because maybe I ask the question like this. So if you take, so we have a fidelity between two states, right? And then we do some processing with the states. So we apply a map. What is the relation between these two fidelities? What do you think?
They are equal.
Are they equal?
Well, for the case of the distances, one was smaller than the other. The
yes.
left-hand side was greater than the right-hand side.
Greater, yes. And now the fidelity is like the opposite of a distance, right? So you should and then it holds. And this is so by processing your states, you cannot increase or cannot decrease the fidelity, right? So you can make the states further away. And once you have this definition, it's trivial because before we see that, well, since my fidelity, I can see it as kind of the best possible way to measure the states and get the classical fidelity. Then of course, this one particular way to do it is first apply this map and then do something else. So this cannot be bigger than this because it's included. So the kind of all the measurements which I do by first applying the channel doing some measurements, actually they are less than all possible measurements, right? So kind of the minimization here takes the argument fewer possible PUMs than here. So obviously this should hold, right? So same thing for the trace distance with changing the thing, changing the sign here because it's not a distance, but it's a fidelity, right? So first thing. Next we will, what's the time? Okay, next we can discuss what is the relation to trace distance. Yes? So let me, maybe first before we discuss this quickly, I'll just give you some, another statement of this trace distance, and this will allow us to recall something about entanglement. So are you all guys familiar with tensor products? Because of course last semester we've seen how to treat like when you have two systems. How do you find a state on two systems? Like Alice and Bob. Is it fine for everybody or?
Yes, it's clear.
Yeah.
It's fine for everybody, so I don't need to recall. Okay, then of course let's before I give you another interpretation of the fidelity, let me recall what is a purification. So do you know what is purification? Purification of a state. So let me just have a system, so a quantum system A on some Hilbert space, some Hilbert space with dimension n+1. Okay, so let me take a row A. Now, you remember that we always said, okay, this state is mixed. Why is it mixed? There are two ways kind of to see it. Either it's really just some random preparation. So somebody just throws a coin and prepares the random state. So there is some mixedness, or it's actually just some pure state on a bigger system where, however, it's traced out apart. Okay? You remember the stories, I guess. So a purification of row A is precisely basically a pure state where if you trace apart, you recover the density matrix. Okay, so your purification of, so if you have a system A and then we just introduce an auxiliary system, so introduce the same system, introduce a similar system, system B, all right, with the same Hilbert space. Now we can define their joint Hilbert space. So the joint Hilbert space will be a H, so let's call it HA here and HB. Right, so we have the total Hilbert space is just a tensor product. What is the dimension of this guy, if you remember? Right, so the dimension of each of them is n+1. What is the dimension of the tensor product? Come on, take a guess. No? Okay, if I have two qubits, what is the dimension of, how many orthogonal levels are there? Well, so I think you don't remember that well then, what is the tensor product? Okay, so basically we have, so if you have a bit, so let me just recall it to you. So if it, this thing I think to see that as a basis. So if you have a basis for HA, yes, then the way we specify a state, a product state in this Hilbert space is just saying, okay, this is the state of Alice and this is the state of Bob, right? And we can just basically write them like this, like so A, so one state is just like, for example, A, B, no? And then the orthogonal states are all the states which are kind of mutually incompatible. So at least A and B are really distinct. So in other words, we have the tensor product basis, right? So the tensor product basis is just defined by, so if you have a basis 0 and for Alice, this is the basis for Alice, and we have the same for Bob. Then the basis for the tensor product space, for the tensor product Hilbert space, is just given by all the combinations thereof, right? Because they are all orthogonal. So in other words, I, Alice tensor, J Bob, with I and J both go from 0 to n. Now, since when you see this, what is the dimension of this Hilbert space? No? Well, obviously there's like n+1 squared, right? So it's just the square of the dimensions. That maybe you should have another some tensor product then again, because you don't seem very familiar. Or you just don't want to answer. I don't know. Do you want an exercise or lecture?
It's clear now.
Clear?
Yeah,
I don't know.
now it's clear.
Very well. But maybe we can give you an exercise, not so you just remember this, because it was a year ago, or at least a semester ago. All right, so Yes. So a purification of a state rho A. Purification of a state rho A is a pure state on the joint system, right? So it's a pure state on that end product, and it's called psi. Let's just call it psi. And if such that, so it's such that when I trace out, so this is the state of Alice and Bob, of course. So such that rho A is the state which I obtain when I trace Bob. So I take this pure state, right? Okay. This is just the definition. And just to see that it's possible always to find a purification, if you have an infinite space of the same dimension for Bob than for Alice, well, it's actually very simple. So let's just take the state rho A, and we just diagonalize it. So this is just given by sum of P K, and right, this is diagonalization of the state for K equal to from 0 to n, the dimension of the infinite space. Now, okay, do you take a guess what is the purification? Well, it's basically just sum of one possible purification is just take this state. So for Alice and same K for Bob. Now, do you see that when I trace Bob, this will be the same one? So let's just do it. Trace Bob, psi psi. Okay, so trace for Bob is just, we said, basically just sum of, I choose a basis, is basis invariant, but for example, I choose a basis, the computational basis for Bob, right? And then we have the state. Yes. So this thing, you see that basically here we have a sum over, well, this will be very small. So let me write it. So this thing is sum of L Bob of sum of K, PK square root KK, K Alice, K Bob, times sum of, for example, J, PJ, J, so Alice Bob, L Bob. Of course, here we get the delta, so this acts on, right, this is a cat which acts on, this is a bra which acts on Bob's cat, and it gives a complex number, and it's actually a delta because it's a basis, so we get it then sum of L, J, K of, yes, PK, let's put it like this, PJ, then KK, or no, LL, and delta LJ. So it's really just this PL, L for Alice, right? So when you get the state, you really get the, if you trace out Bob for the state I wrote before, you really get the state rho A of Alice, partial state of Alice. Okay. Now, is it a unique purification of the state? What do you think? So remember, we had rho A is equal to the sum of PK, K, K, and the purification was, now it's on Alice and Bob. Do you directly see a way to find another purification of the state? To find another state like this, which also gives you this rho A when you trace out Bob. Do you have any clue? In other words, what can I do with Bob? For example, you agree that if Bob just changes the basis or applies the invertible transformation, it won't change at all the partial state of Alice. Right? Actually, whatever he does, it won't change the partial state of Alice. All right. So, for example, you can just take a unitary transformation here and apply it on Bob's side. This will also be a purification. So it's not a unique. So this gives a state, but of course there is not a unique purification. Now I'm telling you all this because, and I think we'll have a lecture on entanglement where we'll come back to these things a bit. later on. But why I'm telling you this is because there is another very nice interpretation of the fidelity. This is called Ullmann's theorem. Ullmann's theorem. And this just tells you that Ullmann's theorem. Okay, and the Ullmann's theorem tells you that when you have the fidelity of two states, rho and sigma, this is actually given by the maximal fidelity over purifications. And this will show in exercise eventually. It's nice because it allows to solve psi 1 and psi 2, where trace of, so these are purifications, so where psi 1 is purification of rho and psi 2 is purification of sigma. Okay. We'll see the proof in the exercise. It's just, is it clear what it means at least?
Yes, it's clear.
Yeah. So you add an auxiliary system of the same dimension. You define as pure state, and then the distance between the maximal fidelity between these pure states is actually given by the fidelity of the mixed states on partial systems, right? So it's a nice result because we'll just use it to relate fidelity to trace distance in one direction. And the proof will, I think we'll just give an exercise on this, either now or later when we're going to talk about entanglement. Yeah, so final thing today, we have like 20 minutes left. So the final thing would be to just kind of close this chapter on distances, right? And to do this, we just see how they are related. So how is the trace distance is related to the fidelity. So relation, as we've seen before, this partially for probability distribution. So relations between D and F, right? So the trace distance and the fidelity. Okay, the first thing to do is to see what we have for pure states. Because for pure states, actually, everything is captured by their overlap, right? So let's take two pure states. So one is pure states. Pure states. So for this thing we just seen before, that for pure states, the fidelity of two pure states, psi and phi, is just given by the overlap, right? Okay. So for the trace distance, it's a bit more tricky, and in fact, we did something like this last time because we've seen the qubit example. But let's do it again. Also, for what is the trace distance for two pure states? Well, for two pure states, the trace distance between rho and psi. So one way to see it is basically, let's just, so these two states, they define actually a two-dimensional subspace of the Hilbert space. So we can always say, let's call psi is equal to the vector 0, right? We just define the basis like this, and then phi, right? We can just basically have two parts. So let's just take it. We take the projection onto psi first, plus the projection on everything which is orthogonal, right? So this one, and we apply it on psi, on phi. Okay. Then you see that we just get something like psi phi 0 of psi plus the rest. Okay, so plus 1 minus this thing. So this will be some orthogonal state, obviously, because we subtract all the parts along this direction. So we'll get something like psi orthogonal with some coefficient. In other words, it's just some alpha 0 plus we will define this beta 1, an orthogonal part. Okay. So if you define a basis like this, where 0 is defined by psi and 1 is defined by the orthogonal part to psi of phi, then we can just write these vectors in a vector representation. So the states in vector representation. So we'll just get well, psi is just equal to 1, 0, right? And phi is equal to alpha beta, where it's also normalized, of course. So now we can easily write the trace distance, because now this thing is, so the density matrix, the projectors now is psi is 1, 0, 0, 0, and phi is, so alpha square, so projector on phi is alpha square, beta square, alpha beta, and alpha beta, alpha star beta, and okay. Just do it like this. Fine. Also now basically you see that alpha square plus beta square, this is 1, so we can just say this is cosine theta and this is sine theta, the absolute values here. All right, and now there's a phase here because there's a random phase, which is actually relevant to the. So the trace distance, just by definition, is the distance. So by definition, this is just 1/2. If you remember, trace of the states, so the density matrices. Okay. Now we use this basis we just defined to compute this trace distance, and in this basis we just get that this difference is 1/2 trace of the following matrix: 1 minus cosine theta squared minus sine theta squared, cosine theta sine theta with some phase, cosine theta sine theta with some other phase. Okay, and of course the absolute value, the trace of the absolute value is really just the sum of the eigenvalues, right? So just 1 minus cosine is sine theta. So you see here that this matrix is nothing else but sine theta square sigma z. So we get 1/2 trace of plus there is a component cosine theta sine theta cosine delta sigma x plus cosine theta sine theta sine delta sigma y. Okay. So we need to find the eigenvalues of this thing. But this is just the Pauli matrix, right? So basically just see this is a vector times the Pauli, times the vector of the Pauli matrices. So very simply we get then this the trace, so right, so we have now here we have something like 1/2 trace of the absolute value of n times the Pauli matrix. And this, you know, that basically it's just another Pauli. So it's so you can put the rotation here, which is diagonalizing it. The trace is mirrored in this. So we have this is just same as trace of the absolute value of n and minus n, right? Which is simply equal to n. Is 1/2. Check. So we just have to find the norm of this vector. And this is just sine theta square, cosine theta sine theta, cosine delta, cosine theta sine delta, and norm. This is n. Okay, so just a very, which is a square root of, yes, sine theta 4 plus, here you see we get cosine theta square, sine theta square, and we get cosine delta square plus sine delta square. Okay, which is 1, so I forget it. And here I can just factor out the sinus. And we get this is equal to sine theta square times, this is 1, times sine theta square plus cosine theta square, which is again 1. Okay, so this is basically sine theta square square root or square root of 1 minus cosine theta square. Right? Are you with me? Or did you guys left?
Yes, but can you wait a second?
Sure. Shall we wait, really?
Now it's fine.
Okay. So yeah, and just since the vectors are 1, 0 and cosine theta sine theta with a phase here, basically the fidelity, you see this is the overlap of the vectors is just cosine theta. So this is equal to 1 minus f square root. Okay. Yeah. So for pure states, it's very easy. For pure states, there's just basically one number is overlap. And we get that the fidelity is just given by the overlap of the vectors, phi psi. So fidelity of phi and psi. Phi and psi is the overlap of the vectors. And the trace distance is equal to 1 minus the overlap square, as we just seen. Yes? So there is one-to-one related, right? It's just a simple formula you use. And it's equivalent to fidelity because they equal or trace distance. However, how do we, what happens for mixed states? Well, for mixed states, something we can use is precisely this Ullmann result, which we just seen. And the Ullmann result said that there is a purification, right? So we said, let's look on the fidelity, right? So the fidelity between sigma and rho, well, it's equal to the fidelity between two pure states, which are purifications of rho and sigma. Okay. And now this is for pure states. So we know that the distance, so the trace distance between these two pure states is just given by this formula, right? So the trace distance between psi or between the purifications and phi, this is just equal to 1 minus f of psi and phi, which is equal to rho and sigma. Okay. So here this is Ullmann theorem, which we'll prove later on. And this is what we just proved now. So for pure states, there's equal, and moreover, since we use purification, this is equal to the state. But now, how do we go from these purifications to the states themselves? Well, we can just trace out Bob. Tracing out Bob is like a processing, you know. So when we do this tracing out, okay, so we just see here, let's take D here of trace out Bob for the state psi. So this is like a quantum map, of course, right? And trace out Bob for phi. Okay, so, and these things are equal to rho and equal to sigma. And what we know is that since we go from here to here with the channel, in general, the distance can only decrease, right? So the distance here between the states, it's actually larger. It's larger or equal than the distance between the things we already traced out. Right? You see this, I guess. So for purifications, there is equality. Now, if you trace out here Bob, then we get the states. But since we did something, in general, the trace distance decreases. So we get this, the nice result that D for rho sigma is in general smaller or equal than 1 minus f square of rho sigma. Okay. And this is tight for pure states. This is one direction. So now we get our result in one direction. Now let's get the other direction. Is it also related to the other? So can we find a formula with a fidelity which actually lower bounds now? Which lower bounds the trace distance. And actually we also can, because this we do it the following way. So the other direction. We do it like this. Well, we know that we also proved, this was the length we proved last hour, and even more than this, that the fidelity between the states rho and sigma, right, this is given by the minimal one between probability distributions. Okay. Yes, so let's now just take these probability distributions for which is the case. So we just take this P of n for which this is exactly saturated. But then last time we've seen that we had a relation between the trace distance and, so what did we see? I think we saw that 1 minus f is, wait a second, how, what's it? Mean square. This was at least, we've seen this, right? For classical probability distributions, yes. So we've seen that for pure classical probability distributions, we've seen that this is actually a lower bound on the distance between P and Q. Okay? So we can just use it, and we use this probability distributions, and we say, okay, well, then by using, we see that for these probability distributions, we'll just put 1 minus here, 1 minus here. So yes, like this. Then they are at least less distinguishable. So this is from last lecture here. And finally, well, we just noticed that, okay, this is a trace distance between probability distributions. For some PUM, not necessarily the optimal one. So in general, this distance is smaller or equal than the distance between the states. Okay. So now we get the thing in the other direction. So we have 1 minus f of rho and sigma. It's more equal than the trace distance between rho and sigma. Okay, and we just seen before that it's also upper bounded like this in the other direction. Okay, so now we have basically all the relations we need between these two quantities. Right? Now, you remember why the trace distance or why the fidelity was useful in the classical case? You remember we argued that like fidelity is easy to compute for many repetitions because you just get a product probability distribution, and the fidelity is just like for a product is just a product of fidelities. Actually, here it's again the same story, because if you take the fidelity of a tensor product of two states, right? Well, you guys basically you see that this just taking the formula again. It's just the same story here. So we have square root of sigma and square root of rho, square root of rho. It just takes the formula, the definition, right? Times square root of sigma tensor square root of rho sigma, sorry. And this is just nothing else that because it's just a tensor product. This is just a trace of the square root of, well, not necessarily the same distribution, by the way. So we get a rho tensor Is this clear what I'm doing here? Because again, we're using tensor products here, and I'm not sure now you're familiar with this.
It's clear.
Right, so this really acts on Bob only. So I can like sigma, I write it as sigma times the identity. This is identity and sigma, and then it just acted there, right? So it should be clear, right? And then this is just a trace of Alice and trace of Bob of square root of sigma rho sigma for Alice, tensor product. Same thing for Bob. So of course it's just a product of traces, right? So we get trace of Alice of this certain times trace of Bob on the same thing. So you see that fidelity as well is just so in summary, the fidelity of a tensor product is again just equal to f of sigma and rho squared. So I'm telling you all this because again, and we'll use it in the exercise now. What's nice is that if you repeat many times, if you have a scenario where we have we repeat the measurement many times, so we have, for example, many copies. We have many copies of states rho, right? And many copies of state sigma. And we measure them individually. We'll see it also in this exercise. Then at the end, the trace, you see, I can see that the trace distance between this kind of big state with many copies. This is, I can bound it in one direction or the other with the fidelity of the state with many copies, which is just a product of the fidelities. Yes? In other words, we see that when we have many repetitions, the fidelity, the trace distance between these guys here, this will be comprised, sorry, and it will be, okay. You see this is at least given by 1 minus f to the power n, between the individual states, and at most by 1 minus f to the power 2n individual states square root. So again, we can use the fidelity as a good quantifier of how well we can distinguish the states in many repetitions, right? So actually, this is very nice because, for example, now you can, I think we do the same exercise as last time we did, but now with many repetitions. And there you will see that it's a bit different because the optimal time even for a single repetition is not the same. Right? So now we see also the one meaning of this fidelity is that actually it allows you to bound some useful quantities, like what is the probability to guess which field is there, is it on and off after many repetitions. Okay?
And so why is there no square root on the left side and the square root on the right side in this inequality?
There is no square root here, and there is, what do you mean?
Is that correct, or?
Yes, it is, yes. Why?
It's like before, without the n.
It's like before without the n. I guess it's the way I do it is actually you just plot them and you see which one is bigger, right? Because you're never sure. But yes, because this is what we've seen previously, that the distance is at least given. This is what we did for classical one, right? Last week.
Yes.
So there we really use it so that the distance between the states is at least given by this fidelity. Right? Now this week we also proved this bound. So just now, basically.
Okay, thanks.
So we have the two now, and actually this will be useful in the exercise for this week because the idea was to do exactly something like this. So yeah, well, you will read the thing. Okay, and yeah, so we took now two lectures to see these distances, and now basically we will close this, right? But I think it's nice because actually most of them we will use them also later on to do some other metrology, right? This is so far the only kind of metrology class we consider was really guess if the field is on and off, or guess between two states, or guess between two states which are in a tensor product, something like this, right? And yeah, we will continue with this. So I realized this fidelity, it was a bit technical, this proofs. Yeah, sorry for this. It's just like this. It's not can't make it easier. Yep. So do you have maybe some questions or comments? No?
Yeah, on this last expression, we consider several like capital N differently prepared states. So I don't know if I can interpret that correctly. We're having N equally prepared states for rho and sigma, and we're just actually computing over several shots of these identical states. Is that correct?
It's so here the way I wrote it here is actually exactly the same states, right? Because it's just a tensor product N. So this is really just like there are N systems and they're all identically prepared in rho. But of course this bound here is to hold also for differently prepared states. So in other words, for example, we have the fidelity of so then it will be like if you have, like, for example, different copies, right? Rho 1, let's say, and rho 2, etc., and etc., right? And we have sigma 1, sigma 2, and so on. This will still be just bounded by the product of fidelities. So we'll have here 1 minus f1. So f1 meaning the fidelity between rho 1 and sigma 1 times f2 times fn. Okay, is it? Yes, and here we'll get the same story because the fidelity of this tensor product state, even though they are different, is just really given by the product of fidelity.
Yeah.
Then we can use both bounds for the global states.
Okay, it's clear. Thanks.
Yes. Moreover, actually, there is now something. The question you ask is it so to get this fidelity now, right? The global fidelity. Do I need entangled measurement, or can I just measure individually the copies? Okay.
But that would depend on how we actually prepare the states of rho and sigma, if they're entangled or not.
No, they're not entangled because in a tensor product, right? So all the sigmas, I mean, it's just across the copies. So we have now n copies here, and this is just the product state. So in principle, it could be that the optimal measurement here, which allows you, because this is the fidelity of, which allows you to achieve the state here, is just an entanglement, but actually it's never the case, and you also see it in the exercises. So you can attain kind of this fidelity for the copies by just measuring individually each copy, right? So you can really think of this scenario as I have n copies and I measure them sequentially, and it's still, this bound still holds. Okay, I mean, yeah, so I really will explain it in the exercise.
It's clear. Thanks.
Clear? Okay. Yes. So that's it.